Okay, I don't want to be saying this guy's principle all the time, so let's see how to pronounce his name.
Le Chatelet's principle. Le Chatelet's principle. Le Chatelet's principle. Le Chatelet's
Okay. So Le Chatelet's principle. Why is this important? Take a look at a can of Diet Coke. It's been sitting there for a long time. It's at equilibrium, okay? Now, once you pop that top open, the system has been sitting there for a long time to achieve that really high pressure that's in the can. So when you pop it open, you release all that pressure. Now the chemical system has to respond to try to get back to equilibrium. So you get all these bubbles. With the greenhouse effect, this is a really complicated equilibrium. We are influencing the amount of carbon dioxide in our atmosphere. And look at all the simultaneous equilibria that are going on here. For greenhouse effect, carbon dioxide is a gas in our atmosphere. It acts like a heat trap. So all the visible light you want can get through and travel through the carbon dioxide. But in our atmosphere, that carbon dioxide is a heat blocker. It won't let the heat back out. And so it ends up trapping heat in our planet. So the problem really is that if you want to remove carbon dioxide, fine, we drive less and we make all these changes, maybe with fusion and all these things. It's going to take 100 years for us to see any effect. Temperatures are on the rise. If you believe temperatures are on the rise because of the greenhouse effect, it's going to continue right now for 100 years no matter what we do right now, because that's how long it takes to remove carbon dioxide from the atmosphere. So that's why it's kind of a big deal. If it's really going on, we better get on it. The Chatelet's principle, what is it? Okay, we have a reaction and an enthalpy for that reaction. What is the expression for Kc? Remember, Kc is just products over reactants and raised to their stoichiometric powers. So we have D over A concentration and the concentration of B squared. Hopefully you left out C because it's a solid. Okay? If the above reaction is currently at equilibrium, what could be done to make the system not at equilibrium? Okay, well, I think it's easier and easiest maybe just to use the equilibrium constant expression to answer these things. When the concentration of D divided by the concentration of A and B squared equals this number, Kc, whatever it is, you know you're at equilibrium. So just do something to change one of these concentrations. Just change one of those concentrations and you're no longer going to do the math and get Kc. You're going to get a different number. Well, that means you're not at equilibrium anymore. Okay? That's really the only thing you got to do. So how could you change those numbers? Well, we could add or remove anything in that Kc expression. D, A, B, right? Change any of those amounts, and you are going to no longer get that Kc number, and you won't be at equilibrium anymore. Notice that C isn't listed, right? Because C is not in the equilibrium constant expression. It's a solid. Its concentration is the same no matter how much you have there, so that one doesn't matter. Okay, there's one other thing you can do here. Well, really two other things. You have a gas, so that means besides adding and removing those three compounds, you could change the pressure. Right? Because you have gases present. Just like in the can of Diet Coke, you have gases present. We could add or remove some heat, and that's the last one. And why do I say that? Because we know that heat is involved in this reaction because they gave us a delta H. Do you remember how this works? Positive meant it was endothermic, and heat is a reactant or a product. Heat is a reactant, right? So add or remove this reactant, heat, and you'll no longer be at equilibrium. So those are some things that'll tell you as to whether you're at equilibrium or not, right? But which direction are things going to shift? That's where this next problem comes in. The below reaction is at equilibrium. Will more or less D be attained when each of the following occurs? So now we're interested in seeing what will be the effect on something if we go off of equilibrium. Okay, let's see how this works. We're going to, in this first one, we're going to remove some A. Now remember, K's, our equilibrium constants, are always products over reactants, right? And when you divide those two and you get this number, you know you're at equilibrium. Okay, that's how the game works. If we're going to remove some A, that now means we don't have enough what? Reactant or product. If we remove A, this number's too small. Right? Because we removed A. A is a reactant. So that amount of reactant is too small. The equilibrium, according to Le Chatelier, it's going to shift. It's going to shift so that you get more reactant because you don't have enough. So it has to shift in that direction. Right? It has to shift and form more reactant because we removed some reactant. Well, if it's going to shift in that direction, C and D are going to react. Their amounts are going to go down because you need to create more A, and you're going to create more B too. So that means the concentration of D decreases because we removed a reactant. Okay. How about if we remove some C? Okay. Remember, Kc, products over reactants, okay. Now we're removing some C. C is a product. So now our products are too low. We removed product. So if the product is too low, now the equilibrium has to shift to create more product, right? So we can get that Kc number back. So it has to shift in that direction. So if it shifts in that direction, the amounts of A and B are going to go down, and the amounts of C and D are going to go up. Okay. How about the next one? Add an inert gas to increase the pressure. Okay. Kc is products over reactants. And you should think, well, what the heck? Pressure isn't a product or a reactant. Yes, it is. How is pressure generated? Pressure is generated by gases, right? So it doesn't matter whether you're a reactant or a product. You generate pressure, okay? So take a look at the number of gas molecules. We have how many gas molecules on this side? 2, right? How many gas molecules do we have on this side? 2. So it's the same pressure on both sides. On both products and reactants, we have the same number of gas molecules. Pressure doesn't matter then. There is no high pressure or low pressure side. And we'll see this again in the next problem. But here there's no change. Okay? And the last one. Increase the temperature. Okay? Let's clean this up a little bit. Where is heat? Is heat a reactant or a product? Right? I think this still works. Kc is products over reactants. It's the same argument, same logic. Is heat a reactant or a product? We're increasing the temperature. It's negative, so that means exothermic. Heat is a product. So now that means we have too much product. We have too much product. Right? Because heat is a product. Heat's a product. We're adding it. We have too much product now. So the equilibrium has to remove that excess stress. It has to shift towards reactants. So that means C and D are going to go down. A and B are going to go up. Concentration of D will decrease. The amount of D, or its concentration, whatever you like to say, decreases. The lower reaction is at equilibrium. Will more or less oxygen gas be present at equilibrium after each of the following? Okay, so we're after this oxygen now. We are going to remove some diphosphorus hexoxide. So recall that Kc is always products over reactants. Right? If we are removing diphosphorus hexoxide, we have too little reactant. We need more if we want to achieve that Kc number. So if the amount of reactant is too small, it has to shift to produce more. So that means the amount of oxygen goes down. Because we need to produce more reactant. Remove some phosphorus solid. Did you catch it? Solid, no effect. No change. It's a solid. It doesn't even show up in the Kc expression. Add an inert gas to increase the pressure. Pressure is odd. In other words, what creates pressure? Gas molecules do. So let's just take a look and see who's producing the gas. Is it the reactants or is it the products? So count up the gas molecules on both sides. On the reactant side, I have one gas molecule. I'm just looking at the stoichiometric coefficients. On the product side, I have how many gas molecules? 3 gas molecules. So when I increase the pressure, let's go back to our argument here. Products over reactants. The system has been sitting there and it's at this nice happy pressure. And now we're going to increase the pressure. So the system has too much pressure now. It has to relieve that pressure. So on the product side, we have 3 gas molecules. On the reactant side, we only have 1. Well, let's shift then and form reactants. Have those 3 gas molecules turn into 1, thereby reducing the pressure. You have less gas molecules. So we're going to shift then to the reactant side. That means oxygen has to decrease. Increase the temperature. So figure out where heat is. Is heat a reactant or a product? Because it's the same logic. Kc is products over reactants. Now I know heat doesn't show up in the Kc expression, but remember, it's positive. That means endothermic. So heat is a reactant. So if we add heat, we have too much reactant. So the equilibrium has to shift to remove that stress, right? Remove that extra heat. We're going to form more oxygen. Oxygen will increase. What would you expect the general temperature and pressure conditions for an optimum yield of nitrogen monoxide in this reaction? So we want maximum of this stuff. Okay, let's do temperature first, because I think that one's easier. Temp. Where is the heat? Is heat a reactant or a product? enthalpy for the reaction is less than 0. So that means it's exothermic. So that means heat has to be a product. Okay? So if we're going to make our argument, remember, Kc is products over reactants. And what we're after is a product. We're after this NO. So if we want to form more product, right, let's remove this heat. Let's remove it. So then the reaction would shift in that direction. So let's remove heat. Let's remove the heat. Does that make sense? Remove the heat, because heat is a product. That means we will have too little of the product, and the equilibrium will have to shift towards products. Okay, so if we want to remove heat as a product, you want to remove it, does that mean things are cold or hot? If you're removing heat, that means cold, right? Cold. Cold temps. So that's one of the answers, cold temps. Now, the other one, pressure, right? So pressure, remember the game? The game was to figure out those gas molecules, okay? Over here, how many gas molecules? 9. 9 gas molecules. Products, how many gas molecules? 10 gas molecules. Okay? So again, remember, equilibrium constants are products over reactants. Okay? We want maximum NO. So do we want a high pressure or a low pressure? Okay? Just pick one and see what the effect would be. Just pick a high pressure. Okay? If we have a high pressure, the system's going to respond to reduce that pressure. So it's going to respond by going away from where there's a lot of gas molecules and go to where there's less gas molecules. So if we have a really high pressure, it would shift towards the lower gas molecules side. It would shift over here with high pressure. Because there's only 9 gas molecules on that side. It's not much lower, but at least it's something. So is that the way you want to go? No, it's not. Because that'll remove NO. That'll reduce the amount of NO and water. So we want to increase the amount of NO, so not a high pressure, but a low pressure then. So cold and very low pressure. Why is the balance a poor description of equilibrium? Well, remember, equilibrium is dynamic. You're forming reactants and products simultaneously, but the amounts aren't changing over time. So there's no way to make this dynamic. You can't show that things are dynamic. And you can't show that Le Chatelier's, you can't show dynamic equilibria. That idea of dynamic equilibria is what is key to Le Chatelier's and forming equilibrium. So it's really kind of the same answer for both of those. It's just not dynamic. Okay, let's do some math review. How would you solve for the variable A in this expression? Okay, and I just want to develop some good habits here. So do you remember the diagonal story? You want to solve for A. So you want to get A by itself on one side or the other. It doesn't matter, and it has to be on top. Well, it's already on top, so let's just move C plus D to the other side, right? And we will be really close. We'll have A plus B, E plus F. Bring the C plus D up there with it. We have G plus H still on the bottom. Now all we have to do is what? Subtract B from both sides. E plus F, C plus D divided by G plus H, whole thing minus B. Okay? How would you multiply through this? So some of you do your FOIL thing. I just multiply through by A, then I multiply through by B, and I'm done. So I'll multiply through by A. I'll have AC plus AD. Now I multiply through by B. BC plus BD. Okay, so the idea here with Le Chatelier is identify what's a reactant and what's a product. And that includes heat. That includes the numbers of gas molecules. And see what your system will do to respond so it can get back to that Kc number. So if that Kc does not equal its special number, you're not at equilibrium. You have too much product or too much reactant.